Here we will discuss the adjoint of an operator. So in the previous sections we have derived a conjugate operator T star for a given operator T defined on Hilbert space. So in that section we have done that if T is an operator defined on Hilbert space H to itself, then T star, which is called conjugate of T, this is defined on H star by T star at any functional f, and because T star of any functional f, that also should be an element of H star, which means it is also a functional, so it is defined at every x in H by f of Tx. So basically T star f is just f circle T, composition of f and T. So we have proved earlier that this T star, this is operator on H star, and the mapping T goes to T star from BH to BH star. So we have defined this mapping from BH to BH star, which maps T to T star. This is a isometry isomorphism which reverses products. Reverses product means T1 T2 goes to, or we can say T1 T2 star is equal to T2 star T1 star. So product is reversed, and it preserves the identity transformation, means the identity transformation I goes to I star, and I star is identity of BH star. Similarly, from this operator T star, we can find out another operator T double star, which is defined on H double star. And we have proved earlier that if H is reflexive, then since H and H double star are same, the T and T double star are same by means of natural embedding. If we identify H to be a subset of H double star, then if H is reflexive, then T is equal to T double star. So now we will define adjoint of operator T. So in the earlier video we have proved that for any vector y in H we can find a functional fy corresponding to the vector y, and since fy is a functional, so we can operate T star on fy because T star is defined on H star. And if we operate T star on fy, then we will get another functional because T star is a mapping from H star to H star. So image of fy, let us say that will be fz, because again we have proved that for any functional there exists a unique vector. So for that image vector, image functional, which is image of fy here, for that image functional we can find a vector, find a unique vector z for which that functional f is equal to fz. So we can say fy goes to fz under this T star, and because fz is a functional, so z is a vector in H. So for a y in H we can find a unique z in H. So we consider here three mappings. So firstly, for any y in H, we know fy belongs to H star. Now since this T star, which is conjugate, so T star from H star to H star, so T star of fy, that also belongs to H star. And we know for any functional in H star there exists a unique vector z in H such that that functional T star fy is just fz. So for this y in H we get a z in H. So we include three mappings here. Firstly we go from y to fy, then from fy to T star fy under the mapping T star, and now since this is fz, T star fy is equal to fz, so we go from fz to z. And we define another mapping, and that another mapping that is also denoted by T star, the same symbol T star. And now this T star is defined from H to H by T star y is equal to z, because this y is an element of H, and for this y, applying these three mappings we get a unique z. So we define T star y is equal to z. So this T star is called adjoint of T. Now the question is why we defined these adjoint and conjugate, why we have denoted these two mappings by the same symbol T star. So here this T star denotes the conjugate mapping, conjugate of the operator T. Here this T star symbolizes adjoint of T. But the difference is that this T star is defined on H star and this T star is defined on H. And how we can differentiate between these two T stars? We will check the domain. If T star is applied on F, where F is a functional, that means it is conjugate. If T star is defined on the vectors Y or X, then it is just adjoint. From the domain we can differentiate between the conjugate and adjoint. So from these observations we can say that for every vector x in H, since this conjugate is defined by T star of f at x is just f of tx, so we apply T star at fy for y in H at x. So it will be by definition fy of tx, and fy, this is a functional defined by the inner product of this vector and y, so it is dxy. So from these observations we can write here T star fy at x, this is just the inner product of tx and y. And secondly, T star fy at x. Now since we know T star fy is fz, so we can write here it is fzx. Then again by the definition of fz it is xz, and xz can be written as, now x as such, now z we have defined by T star y, so it is T star y. So we have two different values of this vector T star fy at x. One is this inner product txy and other is inner product x T star y. So we can conclude here that txy, this is just x T star y. So this T is operator defined on H. This T star is also operator defined on H, and this is adjoint of T. So this is the relation between T and its adjoint T star, and this thing is true for all xy in H. So this is a property of adjoint of T, and it uniquely determines this disjoint. Means for an operator T, there is a unique adjoint operator. So we can prove here uniqueness of adjoint operator, which is proved by this property of adjoint. So let us say T dash is another mapping which we can say adjoint of T. So if T dash is another adjoint of T, then Txy will be equal to x T dash y for all x and y. That means from here we can say x T star y, this is just x T dash y, which means x T star minus T dash at y, this is 0 for all x in H. And if this inner product is 0 for each x in H, that means T star minus T dash y, this is 0 for all y in H, because this equality, this is true for each x and y. So whenever this is equal to 0 for all y, that means T star is equal to T dash. So from this property we can say that every vector T, every operator T has a unique adjoint operator. Now we have some properties of the mapping from T to T star. So in the first step, we will prove that this T star is actually an operator. So we have defined a mapping T star on H star. If we will prove it is linear and it is continuous, then only it becomes operator. So firstly we prove T star is actually an operator on H. So we have to prove in this section that it is linear and continuous. So for all vectors y and z in H and for any x in H, we have to prove that t star of y plus z is t star y plus t star z, and for that we start from here x t star y plus z. So by the above results it can be written as txy plus z. So this is txy by the linearity of inner products. So further this is x t star y, x t star z. So this is x t star y, t star z for all x and y and z obviously. So we conclude here that t star of y plus z is t star y, t star z. So this is first part of the linearity. Similarly, we can prove the other part t star of alpha y. This is alpha t star y. So t star is linear. Now for the continuity, we will start here t star y square. This is just inner product of t star y with itself. So now we apply that t star y, sorry, x inner product of x and t star y is equal to inner product of t star x and y. So from that result t star y. This is because of the result x t star y is equal to txy. So again by Chavag's inequality, inner product of xy is less than equals to norm of x into norm y, and further this is less than equals to norm t star y, norm y. Now this implies norm t star y square is less than equals to this. So this quantity can be cancelled from both of the sides. So this is less than equals to norm t, norm y, and because this is true for every y in H, so we can say norm of t star is less than equals to norm t. Now norm of t star is less than equal to something which is finite because t is already an operator. So if t is operator, then norm of t is a finite quantity. So if this is less than equals to this, that means this is also bounded. So if t star is bounded, then it is continuous also. So t star is operator on H because it is linear and continuous. Now if we define a mapping, let us say theta from BH to BH by theta of t is equal to t star. Now this t star is adjoint because this is element of BH. So this is operator on H. So this mapping, this is called adjoint operation. Now we can write definition. this theta defined by this is called adjoint operation on BH.